First, I'm so pleased that I can present my research results here. My name is Cheol Jang from Cass Business School, London. My research topic is lifetime investment and annuitization decisions using multi-stage stochastic programming. I will present our research result in the following order, but due to the limited presentation time, I will deliver only important parts. In introduction, I will state our research question. When it comes to multi-stage stochastic programming, I will compare stochastic programming with dynamic programming with regard to state space discretization and model formulation. And for part 3 and 4, I have selected representative result tables and figures that well describe our main findings. Lastly, our contributions will be emphasized. Let me start with a hypothetical case that describes what a lifetime investment problem is. This 40-year-old man has initial wealth, £80,000 in his current account, and also there are his current investment position, labor income, labor supply, and his retirement and housing plans. Each component is related to from interest rate for his current account to home price for his housing plan. They are virtually time-varying and uncertain, and they can affect his current optimal decisions. So, what solution does he need? The solutions should include optimal consumption levels, investment strategies, and labor supply. Here we will investigate only consumption investment strategies, but labor flexibility is an important factor in the lifetime investment problem. These decision variables are naturally dynamic choices. This means he can change his decisions at any point in time. So our research question is this: how does the investor optimally decide his consumption investment and labor strategies that involve uncertainty? We want to solve this lifetime investment problem by using multi-stage stochastic programming, MSP, since the model or the approach can incorporate sophisticated realistic features so can deliver implementable solutions at the moment. I'm going to talk about how to construct a MSP model. The model can be explained by comparing with a dynamic programming model. For both models, state space discretization is required. If you see the left panel A, it shows a grid method for dynamic programming that is widely used in its literature. There are 3 time points, i.e. 2 time periods, but time intervals can vary. Here, letter R and S are state variables. Let them be gross returns of a bond and a stock, respectively. The grid method divides the state space equally with the given number of points. This figure has a 10 by 6 grid, i.e. 60 points in total at time 1, and another 60 points at time 2. Optimal solutions are determined on each grid point. On the other hand, you can see the right figure, B. Stochastic programming uses a tree structure. We called it a scenario tree. It consists of nodes and edges. The very first node n sub 0 is called a root node. The very last nodes at time 2 are called leaf nodes. Three nodes at time 1 indicate 3 mass points that represent conditional return distributions of the bond and stock. 9 nodes at time 2 also represent the result distributions but conditioned on its parent node. Here P means probability that a given node occurs. Similar to the grid method, optimal solutions are defined on each node. To explain about model formulation, I will describe an expected utility maximization model with terminal worth that denotes capital W. the objective function equation 2.1 subject to a budget constraint equation 2.2 in which optimal risk asset weight X, bond and stock returns R and S control wealth distributions over time. We should transform the equations into deterministic equivalent equations in a nodal form. The transformed objective function equation 2.7 is just rewritten including probabilities that denote P. For the budget constraint, one balance equation and two inventory equations are required. The balance equation 2.9 controls cash inflows from the monetary amount of the bond and stock sold and initial wealth, and the cash outflows from the amount of the bond and stock bought. The two inventory equations track the holding amounts of the two financial assets. They are equal to the total growing values plus net buying values. For clarity, we may add the wealth amount at node N, that is W to N, node N, equal to the holding amount of stock plus the holding amount of the bond. A purpose of this part is to assess whether the MSP model can generate non-academic findings in lifetime finance. So we replicate Morton's results but include transaction fees, management fees, and capital gain taxes. Due to the presentation time, I will only present the result with transaction fees. The Morton type lifetime investment problem is a consumption and bequest utility maximization problem. It has certain lifetime from 0 to time t, time preference rho, power utility functions u and b, and bequest parameter epsilon. Analytical solutions for optimal asset weights and consumption wealth ratio are given under asset return dynamics of geometric Brownian motions. The optimal stock weights X are constant over time, and for a special case, the consumption wealth ratio is also constant. As I showed you, we need deterministic equivalent equations in a nodal form. The way to set up this is similar to what I stated, but there are two things we should note. Consumption at node n, here C to the n, is continuous, but does not change between node n and each children node. And the optimal asset allocation implicitly indicates a buy and hold strategy for a time interval between two consecutive stages. These are variables, coefficients, and parameters that I used for constructing our MSP model. I will skip explanations, but transaction fees are defined by UF for upfront fees and SF for selling fees. For a numerical case, I use 10 different scenario trees for a risk stock and a risk-free cash account. All fees and taxes are set to 0, and we have a 1-year planning horizon with 5 stages. Time intervals are quarter. The individual investor can change his portfolio at time 0, 1, 2, and 3, but cannot change at time 4. Without loss of generality, we can regard this timeline as an individual's lifetime if capital T is, for example, 30 or 50 years till he dies. This result table compares our solutions with Morton's ones. As you see, when the analytical solution for the optimal risk asset weight X is constant at 0.35 over time, our numerical solution is close to that analytical one. And the optimal consumption wealth ratio shows also only a marginal error at stage 4. This table also compares optimal solutions but with transaction fees. When upfront fees and selling fees are set to 1%, 100 basis points, then the risky asset becomes less attractive so that the optimal risk asset weight is almost 10% lower than the no transaction fee case. Also, The fees make the investor reluctant to rebalance his portfolio, so the risk asset weight is increasing over time on average. Optimal consumption wealth ratio is also lower than the Morton's case since actual expected returns of the risky asset is lower. The results are consistent with the literature, so we confirm that MSP model can incorporate known academic findings. Now in part 4, we expand the previous model further by using a vector to a regressive model with Nelson-Cecil term structure and by adding deferred annuities as an investable asset. And introduce an income-focused objective function for an individual investor who is interested in securing his retirement income by purchasing deferred annuities. I will demonstrate each optimal portfolio strategy with deferred annuities as an alternative to conventional life cycle strategies. First, let me define a planning horizon for our numerical case. There is a 40-year-old man who expects to retire at age 60. Similar to the previous case, he can change his portfolio only at time 0, 1, 2, 3, so every 5 years. Here I will use standard actuarial notations to take account of uncertain lifetime, P for survival probabilities, Q for death probabilities. We define an income-based model. It has a certain planning horizons of capital T, in our case 20 years, and it uses power utility U of a secured retirement income increment by buying deferred annuity at node N that starts to pay its fixed nominal benefits from a policyholder's age 60. So by sub dA to the N denotes the unit amount of deferred annuities bought at node N. So the aggregate units of deferred annuities are equal to the total secured retirement income. And the model assumes uncertain lifetime by using survival and death probabilities. The biggest function B is equal to that in previous part. The variables for portfolio allocations X are the unit amounts of asset bought and sold, but deferred annuities are not allowed to sell, i.e. an irreversible contract. In our numerical case, we have 4 assets: bond, equity, cash, and deferred annuities. This bar graph shows average optimal asset allocations over time, which are obtained by solving the MSP model we just defined. The allocations include deferred annuities. As expected, the optimal proportions of deferred annuity value to the total portfolio value is increasing over time. Since our objective function is directly linked to deferred annuity purchases, the average unit amount of deferred annuity hold almost doubles every 5 years. Portfolio allocation to the bond falls over time, but among 3 assets, equity, bond, and cash, the bond has the largest portion in the portfolio over stages. It has a role of hedging to price changes in deferred annuities. Equity proportion increases after first stage. This represents the investor's risk appetite after taking account of uncertainties in bond and deferred annuity prices. The role of cash account is providing liquidity to fund future deferred annuity purchases, especially when the bond and equity are not on good status to invest. As a part of our research project, this presentation can be summarized with the following 3 contributions. Firstly, we have obtained solutions that are consistent with existing academic findings, especially Martin's results. Secondly, we have shown technical advantages of MSB with realistic features such as fees, capital gain taxes, and mortgage. We have investigated all 3 features but not presented here. Lastly, we have constructed an alternative retirement strategy with deferred annuities. I didn't directly state how my research and MSP approach are linked to aging and risk management. That are the conference topics. Instead, I would like to emphasize its potential uses. A simple example is that we can examine optimal lifetime investment strategies using MSP when subjective or actual mortality rates and pricing mortality rates are different. This is related to aging and risk management issues. Thank you.